Now it's your turn. Each scenario describes a gas undergoing a change. Before reaching for an equation, identify which variables are changing, determine whether they have a direct or inverse relationship, and then build the appropriate gas law before solving the problem. Okay, here's the first question. A marine scientist packs a sealed bag of chips before taking a research submarine deep into the ocean. At the surface, the air inside the bag has a volume of 2.5 liters and experiences an external pressure of 1.0 atmospheres. As the submarine travels deeper, the water pressure outside increases. When the submarine reaches its research depth, the pressure on the bag increases to 5.0 atmospheres. What is the new volume? Here's our before scenario. We have a certain number of gas particles flying around in a container and a little bit of pressure pushing on the outside of the container. We can identify our variables as initial pressure is 1.0 atmospheres and initial volume is 2.5 liters. Then things change. The amount of pressure on the container increases. That's symbolized by all of the little red dots pushing down on the container. The temperature stays the same, so the little arrows are the same length. And there's also the same number of particles in the container, but the volume of the container changes. We get a final pressure of 5.0 atmospheres, and we're looking for the new volume. So if we increase the pressure on the outside of a container, it will decrease in size. This is an inverse relationship, so we have to use Boyle's law. I'm going to plug in my variables for each of the letters and then solve for V2, and I get 0.50 liters. Now, hopefully this makes sense because as we are increasing the pressure, the volume is decreasing. And if the variables are next to each other on the same side of the equation, that means that they are going to be inversely related to each other. So we get the initials and finals and solve for V2. Try to do this one on your own. Pause the video. After a birthday party, a student leaves a helium balloon in their warm house. Inside, the balloon has a volume of 4.0 liters at 25 degrees Celsius. Overnight, the balloon is accidentally left in a cold garage where the temperature drops to 5 degrees Celsius. The next morning, the balloon looks smaller. What is the new volume of the balloon? So here's our balloon, and we have a certain amount of gas particles flying around inside of it. The initial volume of that balloon is going to be 4.0 liters. The initial temperature will be 25 degrees Celsius, which must be converted to 298 kelvins. Remember, you need to convert to an absolute temperature unit for these equations to work. Now we're going to cool the balloon down. Notice how we have the same exact number of particles flying around in the balloon? The only thing that's really going to change is the temperature, which will ultimately change the volume. So we're cooling this balloon down, and we're cooling it down to 5 degrees Celsius, which is converted to 278 kelvins, and you can see that the balloon gets smaller. So as you're cooling down the balloon, the particles are moving slower, and they're hitting the inside walls of the container with less energy, which makes the volume decrease. This is a direct relationship. Cooling it down causes the volume to decrease. So we can use V1 over T1 equals V2 over T2, and then if we plug in all of the variables and solve for V2, we get 3.7 liters. Remember, for this equation to work, we need to convert to kelvins, and the number of particles and the atmospheric pressure need to be held constant. Okay, on to another practice problem. A spacecraft contains a sealed oxygen tank. Engineers know the tank cannot expand, so the volume stays constant. At a normal operating temperature of 20 degrees Celsius, the oxygen tank has a pressure of 150 atmospheres. Now, a malfunction causes the tank temperature to rise to 80 degrees Celsius, and the warning system detects a pressure increase. What is the final pressure? So here is our oxygen tank with the particles inside of it. It's sealed shut. We're not changing the volume, and we're not changing the number of particles in it. The initial pressure is 150 atmospheres at a temperature of 20 degrees Celsius, or converted to kelvins is 293 kelvins. Now, the temperature is going to increase for this tank. It's going to increase all the way up to 80 degrees Celsius. So the new pressure inside that tank is also going to increase. And the reason it does is because we still have the same number of particles, but now they are moving faster. And you can see that because I've represented that with longer arrows. So we're finding the new pressure. The final temperature of the tank is 80 degrees Celsius, and we have converted that to kelvins to give us 353 kelvins. Okay, so if the temperature goes up, that causes the pressure to go up because the particles are now moving faster and hitting the inside walls of the container with more energy. So this is a direct relationship, which means we will use P1 over T1 equals P2 over T2. Now I'm going to plug in all my variables here and solve for P2, and I get 181 atmospheres. Okay, here's the last one. A chemistry professor is setting up a giant inflatable dinosaur for a science event. The dinosaur initially contains 12.0 moles of air and has a volume of 300 liters. Unfortunately, it's not big enough, so more air is added until the dinosaur contains 20.0 moles of gas. Assume the temperature and pressure stay the same. What is the final volume? So here is our dinosaur with just a little bit of gas in it, 12.0 moles, and a volume of 300 liters. Now we're going to inflate that dinosaur with more gas, so we're going to include more particles in the drawing here, the little representation of it. Increasing the number of moles of gas in this dinosaur increases its volume. This is a direct relationship, so we can use the equation V1 over N1 equals V2 over N2 to solve this problem. I'm going to plug in all my variables and solve for V2, and I get 500 liters. And that should make sense because if we add more gas to an inflatable, it's going to inflate more and it's going to expand and the volume will get bigger. Okay, as you work through these problems and others, remember that the equation is not the starting point. The relationship is. Once you understand how the variables interact, the math becomes so much more intuitive.